Hello, students. Today we want to talk about polynomial functions. Now, there are lots of ideas that we can consider when we talk about functions. Theory of equations is a very important topic, and you will use that when you get to your prerequisite course, pre-cal, and also the calculus sequence. But what we want to do today is to basically define what a polynomial is and look at certain characteristics of the polynomial that will make working with them a lot easier. Now, as we continue through the process of looking at polynomials, we will discuss continued characteristics of them. We will talk about ratios of polynomials, and we will think about theory of equations. So we'll break it down into pieces so that it will seem a lot less arduous as we work through it. But polynomials are pretty much everywhere, and we need to have a basic understanding of them. So let me go ahead and share my screen. What I've done is to highlight some of the properties of the polynomial, just so you'll have them for easy access. Now, when we study college algebra, we study the pre-calculus, and we work with the calculus sequence, we tend to focus on the real polynomials as opposed to polynomials that would have imaginary coefficients. So what I've written here is real polynomials, and from the standard notation for the polynomial, I've said that the a sub I will be a real number, and the n here will be a natural number, a counting number. So remember, the little epsilon here means that the coefficient a sub I is contained in the real numbers. And polynomials look exactly like this. This notation here, r bracket x, just means that we have a real polynomial. That's all that means. And you don't have to use it, but it is fairly standard in the literature. So when we look at this, we have the coefficient a sub n times the nth power of x, and this is written in decreasing order. So notice here we have the power n minus 1, and we subscript the coefficient to have the same number as the power. So the a sub n minus 1 is paired with the n minus 1 power of x, and we decrease until we get to the quadratic term a sub 2 times x squared plus a sub 1 times x plus a sub 0, which we call the constant term. So if you like, this is important. This is the so-called constant term. So if you think of quadratics, quadratics are polynomials. Linear functions are polynomials. And this is what we normally call the leading term. And we'll say more about that. So again, polynomials look exactly like this. And in most of our study, we will most likely look at polynomials that have integer coefficients, integers like the natural numbers plus the negatives of the natural numbers. So think about the quadratic equations we've solved. Think about the higher order polynomials that we solved by factoring. All of those instances were, again, examples of polynomials. Just remember, we can't have square roots. We can't have non-integer powers. And when I say integer, I mean the positive integers, the counting numbers. We don't have negative powers in polynomials. We don't have fractional powers. We simply have the natural numbers, 1, 2, 3, etc. And then, of course, the possibility of the constant term, which could be 0. Now, when we think about the degree of a polynomial, ladies and gentlemen, we think of the largest power of x. So if we've got a quadratic polynomial, its degree is 2. Again, the degree is always the largest power of x. Now, one thing that the text often wants to quote to you would be the following term, the maximum number of turning points when you think about the graph. Now, for instance, if you think about a quadratic function that has two zeros, then you see that it will have one turning point. So here's a simple example of the quadratic. Let's say we have a quadratic function that has two zeros. So again, the graph would have to look something like that to pick up the zero here and the zero here. And so we would say that the graph would have one turning point, or the maximal number of turning points would be, in this case, 1, which is less than the degree by 1. Now, what can also happen as the degree gets higher and higher, there aren't necessarily, for instance, for degree 2 or degree 3 or et cetera, we might not necessarily have real zeros that occur with the multiplicity equal to the degree. So for instance, we could have a situation like this. So we've got a fourth degree equation, and maybe it has no zeros, and it looks like this. Okay, so a fourth degree has degree 4, absolutely, that's 4. But again, what we see is that the maximum number of turning points, which could be 3, is not evident in this case. So when we talk about maximal number of turning points, we're just thinking of the possibility that that could include. It is not necessarily going to happen, but it certainly helps us think about the possible shape of the function. So for instance, this could be described this way. Let's just say we have the following. Say it's shifted, so this could be like P of X equals, say, X minus 3 to the 4th power plus a 2. Now, when we look at this, and this is what very interesting about this, notice we have a 4th power here. So this term is always non-negative. That is, the only time that this is 0 is when X is 3. And then, of course, we add the 2. So this particular polynomial would never have any real zeros. And so it would have a shape that would look more like this. Now, this is not exactly, again, what we want to infer, that every polynomial needs a very difficult analysis. But if we think about transformations, if we think about just the standard X to the 4th, it has a similar shape to the quadratic, the even power. And then what we see is we're shifted to the right by 3, and then we have an upward vertical shift by 2. So you can think of this as like the 2 here and the 3 here, looking at this just in terms of transformations. So when we think about turning points, we're thinking about the maximal number that would be possible. And so it doesn't necessarily give us a lot of information. Here we see we just have the one turning point, so to speak. This reminds us of a quadratic function. So when you answer this question as being n minus 1, again, it's just simply a possibility that might occur. Now, one thing that's very important, and I've stressed here, you can now use, like I said, as I described this, your function transformations to get graphs of polynomials that are fairly simple and have this form, or you can make them up yourself. So the polynomial transformations that, again, are realized by the function transformations are universal. So you can continue to use those when they are useful to you. Now, one thing that the author doesn't necessarily state when the polynomial functions are introduced is the factor theorem, even though it is certainly used as a point in the particular section. So what we're going to state here is something you already know, but basically if c is a zero of the polynomial p of x, x minus c must be a factor. Okay, now what does that mean? That means that you can actually factor some power of x minus c like I have here. So if p of c equals 0, then basically by substituting c for x, the polynomial is annihilated, that it becomes 0. So it would have to have this form, that is, it must have at least one factor of x minus c, and then, of course, another factor over here, which is just a reduced polynomial. So again, when you think of a polynomial having a 0, say 4 or 5 or -3, you have to have that corresponding factor so that when you replace x by that particular number, it annihilates the polynomial, just basically converts to 0. So when you think about this and you're looking at exercises and all, consider the factor theorem. We will not formally state it until later, but we need to understand that if a polynomial has a 0, then it must necessarily have this form in order to create the 0 when we actually replace x with c, okay? So again, zeros of the polynomial, very important. The form, the standard form of the polynomial, very important. Notice the standard form here is to write the polynomial in descending order with the powers of x getting smaller as we make our way to the constant term. So that is just a convention. But usually when you write your quadratic equations, you write the quadratic term first. So this is something you're accustomed to. Now, one thing that's very useful, and I've already mentioned it in our lectures covering inequalities, that is the multiplicity of the 0, and that's exactly why I have mentioned the factor theorem here. For instance, when you have a 0, it will occur to a particular multiplicity. If all the multiplicities of zeros are just 1, that would mean that you would have distinct zeros, okay? But it would be possible that the power associated with the x minus c, as we see here from the factor theorem, that this power could be larger. That is, it could be a 2, it could be a 3, whatever. Notice what's important about this is this impacts the quality of the graph when we actually sketch a graph of the function. So let me point this out. Now, this will be something that we can say more about when we have the division algorithm, which is actually the reason the polynomial looks like this here at this point. But that will come with some later lectures. I don't want you to think that you have to process all of this information now. I want you to have the basics at this point. But something very useful that I've already mentioned is the following. If the multiplicity of the 0 is an even number, then the graph will touch the x-axis. It will touch the x-axis. So we could write something like this. Say the 0 is at C, and so the graph just touches. It does not cross. Now, if the multiplicity here is odd, say 1 or 3, it will cross. And we've already used this in our inequalities. So this might be an indication, or it could come this way and go into the positive realm. So we say touch for the even multiplicity, we say cross for the odd multiplicity. And this helps us considerably when we're doing inequalities, because once we establish a more extreme behavior, then we can actually run through the zeros either touching the axis or crossing relative to the multiplicities. So this is very easy to remember, and this is a local result that actually uses the continuity of the polynomial along with the factor theorem and the division algorithm, but we will get eventually. So what I wanted to point out here was a simple example of when we have a polynomial where we have what we call the factored form, okay? Of course, creating polynomials with particular zeros is not that difficult, but having to multiply everything out can be very arduous. And I have an example that I'll show you of that. Now, here's just a basic example where we have a 0 of 3, we have a 0 of -5, and we have a 0 of -2. Remember, if we have the 0, we must have the corresponding annihilating factor. So these are all multiplied. But notice the multiplicity of 0, 3 is 2 even, so the graph will touch at 2. The multiplicity of the 0, -5 is odd, 3, so it will cross at -5. The graph will cross the x-axis. And then we see that the 0 of -2 has even multiplicity, so it will touch at -2. Now, one thing you might think about is when you've got a plus here, you can think of this factor as x minus a -5 cubed. And for the +2, you can think of x minus a -2 squared. So that highlights the fact that the actual 0 is what? -2 here. This highlights the fact that the actual 0 here is -5. But now, of course, if you replace x with -5, this factor absorbs. It is annihilated. It becomes the 0. If you replace this x with -2, it becomes the 0. Okay, so simply writing it this way identifies the actual 0 in the symbolism, just like the 3 is identified here because it is to the right of the negative sign. Here we see -5 is to the right of the negative sign, so -5 is a 0. Here we see -2 is to the right of the negative sign, so -2 is a 0. Now, all this information is very basic, but it is very important when we deal with polynomials and we think about factoring them. And that will be something that we will continue to do as you have been doing when you have been working with your equations. Now, notice here, we can add the degrees of each of the multiplicities. So we get a 2 plus a 3 plus a 2, which is a 7. So the degree of P is indeed 7, and the maximum number of turning points would be less than that by 1, which is 6. Again, not really the most useful piece of information. It's only just a possibility. So we must utilize more information in order to get what we call a reasonable graph. So again, how can we get the reasonable graph? We're on our way, at least using the multiplicities, which we have already talked about, which will help us to graph and also continue to help us with our inequalities. And we know what the form of the polynomial must take if we have a particular 0, which is basically the factor theorem, okay? I've tried to summarize all of this stuff so you have a document of what is important with the polynomials, and we will carry this with us as we continue and always refer back to it. Now, what I've done here is I've added the last dimension, and of course I did all this arithmetic to find the y-intercept. It's kind of interesting how this problem worked out. Now, in order to figure out what happens as x passes to infinity or negative infinity, we simply have to look at what I talked about before, the leading term. Notice the leading term, ladies and gentlemen, has the largest power of x. So when x becomes large, and this is really a calculus problem about continuity and x passing to infinity, or as we say, limits at infinity, this particular term will dominate because the power is the largest, and the other terms will have a negligible effect. So what we want to do is focus on the leading term. So that means the polynomial in behavior will be a sign of infinity. And how do we figure it out? We simply look at the sign of the leading term. For instance, if x is approaching infinity, then we can simply replace x with a positive number and then consider the sign of the coefficient. And whatever we get from that will be the sign that we assign to infinity. Likewise, as we approach negative infinity, we can do the same thing. Now, again, we just simply replace x with a negative number because x is becoming infinitesimally small, and we also consider the sign of the leading coefficient. We assign that particular plus or minus to infinity. So again, the end behavior is just an arithmetic exercise. And you might be thinking, well, Professor, if we have it factored, we don't really have that leading term right in front of us. So let me just show you a quick way to figure out why this particular polynomial has a reasonable graph like this. Now, when you look at this, this is simply a characterization of what the graph may possibly have. It does not have a lot of precision. We don't have the relative extrema identified because this becomes a calculus problem. And in general, ladies and gentlemen, the analysis of polynomials can be very difficult because finding zeros as polynomial degrees get higher and higher can be extremely difficult without the use of calculus approximation. So what we can see here is that when you look at this factored polynomial, we can now see we have an x squared here, we have an x cubed here, and an x cubed here. So we could say the leading term, if you were just interested in it, the leading term, again, we have the -3 here. So we've got what? -3. We have an x squared. Just looking at the powers of x, we have an x cubed, and we have another x cubed. So this gives us a -3. And then, of course, we get an 8, x to the 8. If you were just interested in the leading term. But let me show you why we don't necessarily need that. Now, notice if we check out the zeros, notice we have a 0 at 2, we have a 0 at -3, and we have a 0 at 5. So if you were thinking of letting x pass to infinity, positive values get more and more positive. So if we replace x with a positive number, again, the x here is to the 8th power. That's still a positive number. But then if we consider the sign of the leading coefficient, that renders the number less than 0, negative. So now we can see that the end behavior as x approaches infinity is indeed negative infinity. And then you're thinking, do we need to do the other one? Well, if we didn't have any zeros to contend with, then we would. But notice we have the factored form here and we have the multiplicity. So if we start out here below the x-axis at 5, we have to cross due to the odd multiplicity. But then as we move to 2, notice it has the even, so we just touch, so we still stay positive. But as we approach the -3, we have an odd multiplicity, so we have to cross. So now we can see, and this makes perfect sense, as x passes to negative infinity, we get negative infinity. So we can just state here that the limit as x approaches infinity of our p of x is negative infinity, as we've already established, and the limit, just using the limit notation, as x passes to negative infinity of p of x would also be negative infinity. But that makes perfect sense because notice here, if x is replaced with a large positive number, the sign is still negative. And of course, if x is replaced with a very small number like negative 5,000, the negative is absorbed due to the even power. And so the sign is still negative. So we would expect the graph to drop off on either side to negative infinity. And then, of course, what you notice here is I've got this number 40,500. Well, that's simply the y-intercept. And that it really, when we have high multiplicities here, the numbers get big fast. So if I simply replace x with 0, we have -3. And of course, -2 squared is 4. 3 cubed is 27. And -5 to the third power is -125. And so, of course, the negatives absorb, but then I just broke this down into simpler numbers. Notice here, when we start multiplying, 12 is just 10 plus 2. We can hit that with the 27. And then, of course, 125 we can write as 100 plus 25 and just use the distributive law. So what I've done here, it's easy to multiply numbers by 100, and that was very easy to do. And now notice we've got these numbers taken care of. Then we have to multiply 270 and 54 by 25. So I just wrote the 25 as 20 plus 5 to make these multiplications simple. So there is a way to actually multiply numbers in a very simple way when you break down the numbers using the base 10. And so as you continue to add here, I thought this was an interesting exercise. We end up with the 32,400. And then when we multiply here, we're going to get a 5,400. And then, of course, the 5 times the 270 will give us 1,350. And then, of course, we just keep going. The 20 times the 54 will give us 1,080. And then, of course, the 5 times the 54 will give us 270. And then we can simply add these, because adding the numbers once they're multiplied is very simple. We just do this piecemeal. So at this point, if you look at this, we add these two numbers to get 6,750, and then we add these two numbers to get 1,350. And then now, of course, if we add 32,400 with 6,750, we get 39,150. And then if we add the 1,350, we end up with 40,500. So y-intercepts for polynomials can be very big. You just thinking here, these zeros are not incredibly large, but with the powers here, the values of the polynomials can get large very quickly. And you're thinking, we're just replacing x with 0 and we get this number. So of course the scale here is like minute compared to the scale of the zeros. You didn't even bother to do this except to write the number there, because again, when I made up the problem, I thought, well, this is an interesting problem. I don't want to change it. So just remember, ladies and gentlemen, that when we do this very reasonable graph, we're only using the luxury of having some real zeros here. Okay, this is a very special polynomial. Notice it has degree 8, and it has 8 real zeros when we include the multiplicities. So when we think of the degree of a polynomial, that really opens the door to saying, okay, if we have degree 5, then we should have 5 zeros if we include multiplicities. And that will basically be utilizing the fundamental theorem of algebra that tells us that any polynomial of at least 1 degree has a complex 0. And then we keep applying that result until we just whittle down to a constant. Okay, and so that's why we can always put the leading coefficient out to the left, which we see ends up in the leading term when we do this computation. So again, there's a lot of theory going on here, and what we're trying to do is just get the basic ideas. You can always use your basic transformations to get a graph, or you can use the factored form to plot the zeros and use cross and touch with the multiplicities. That will again give you a big idea about the end behavior without having to check each one separately. And then, of course, once you have that, then you can sketch a reasonable graph. Again, this graph doesn't have a lot of precision. We're not really sure if this is actually the maximum or the graph comes up more and then proceeds down. And we certainly don't know what the level of this maximum is, local maximum. We don't know that. So we just drew a graph that gives a basic picture of what the function is without lots of precision. Okay, so that's what we have to think about when we're doing this. We're thinking that's kind of the shape of the function, but we would need calculus and we need more refined tools to make this function look better. Okay, now the last example that I have here, and I ended up doing more work. You'll see basically in the problems that you do that they say don't multiply things out. But as I looked at it, I thought, well, there are times when you want to write things in descending order. So what I did here is just think of a polynomial that has particular zeros. So we have a 0 of 3, we have a 0 of 1, and we have a 0 of -4. And then I said that the 0 of 3 will have multiplicity 2, the 0 of 1 will have multiplicity 3, and the 0, -4 will have multiplicity 1. And then just as a little extra side item, since I talked about in the past example that I made up, that the y-intercept was 40,500, I thought, well, let me be nicer to you. So what I said here, till we get a unique polynomial, is that I just said the y-intercept is the number 72, which is actually divisible by the numbers here when we consider the multiplicities. So basically, we'll have the leading coefficient, which we don't know. We have x minus 3 to the second power for this 0 in multiplicity. We have x minus 1 to the third power for this 0 in multiplicity. And then, of course, for -4, we have x plus 4 to the first power. Now, again, I chose nice numbers here. That is p of 0. We simply replace x with 0. So we have 9 times the -1 times the 4. That's a -36. But of course, -36 divides 72 is just -2. So now we actually do have a unique polynomial. In lots of the exercises, all they ask you to do is write a polynomial without any additional information. But I always like to give you some extra so you can see where we're headed down the road. The idea is I like to connect the ideas we're working on now with ideas that we're going to see in the future, so they're not so as abrupt when we have to work with them. So now you can see here that we have a unique polynomial. And this is normally where you stop. But I just wanted to show you something here that was fairly interesting about this problem. You can now expand the x minus 3 squared, again, using your algebraic identities, to x squared minus 6x plus 9. And then, of course, here, this is the binomial theorem. If you multiply x minus 1 times itself 3 times, you'll get x cubed minus 3x squared, plus 3x minus 1. And then, of course, you just have the x plus 4. Now, what you can do at this point, notice here, I just multiplied this quadratic factor times the -2. And then from that point on, I just simply hit all of these with these terms, multiplying each of these terms by -2x squared, each of these terms by 12x, and each of these terms by -18. So we end up with -18 times -1, which is +18. Now, at this point, you see I've underlined things here. So I started combining the like powers. So when there's only 1/5 degree here, so that was easy. So we have to combine all the fourth powers to get 18x to the fourth, and then combine all of the third powers, adding the coefficients to get a -60, and then adding all the squared powers to get a 92, and then all the first degree gave me a -66. And of course, there's only one constant term, which is 18. So that was the worst part. Now, of course, we're just left with the x plus 4. So each of these terms gets multiplied by x. That's easy to do. So the 5 becomes a 6, the 4 becomes a 5, the 3 becomes a 4, the 2 becomes a 3, the x becomes a square, and the 18 becomes 18x. And then we hit everything with a 4, but I thought that would just maintain the power. So I just lined them up. The 4 times the -2 gives us a -8, and the 4 times the 18 is 72, and then the 4 times the -60 a -240, and the 4 times the 92 a 368, and then the 4 times the -66 is a -264, and of course 4 times 18 is 72. And so now it's in a vertical disposition where they can be added. And so now this is actually what you end up having to do in most courses. So usually you wouldn't have something maybe this long, but there is no difference if the problem is long or if the problem is short. The distributive law is what you use. So now if we write this polynomial, ladies and gentlemen, in the descending order, this now becomes a problem that we will work on later. That is, we'll start with this and hope to get to this, which will require some new theorems. So now P of x in descending form is -2x squared plus 10x to the 5th plus 12x to the 4th minus 148x cubed plus 302x squared minus 246x plus 72. Now, you would never be given a problem like this to work backwards. I just want to show you that we see the beauty of having something in this form. Okay. Now, of course, if you're going to differentiate this in a calculus class, this would be easier to do. This would require many applications of the product rule. So the idea, ladies and gentlemen, is that if you want to practice just using the distributive law to write this in this form, you can see once you create a polynomial, then you write it in descending form, you've created a difficult problem, because in order to take the problem backwards, you have to actually analyze it. So if you've already made up the problem, you know this is equal to this. But if you don't know that, then you've got to start looking at the coefficients, looking for patterns, and look for rational zeros, which is a major theorem that we will use to actually write what we call the linearized form of the polynomial. So what we call this, ladies and gentlemen, we will later call the complete factorization. That is, we have, and this is a luxury. For instance, we may not necessarily be able to do this, okay? But in cases where we have the disposition of zeros that is very convenient to us, I mean, we have a 6-degree polynomial and we have 6 zeros, including multiplicities, and they're all real. So this is a very special polynomial. And even the ones that are special that have the nice zeros can still be very daunting if we actually had to start with this particular form of the polynomial. So as you're working these examples, I want you to note that you can use the zeros, the multiplicities, you can use the y-intercept, the end behavior, and get acquainted with all of that. And just make sure, ladies and gentlemen, that remember, all the polynomials have this form. All polynomials have this form. And so if you don't have this form, it's not a polynomial. And so just remember, as we continue on with our work, we could have other functions and we can still use this multiplicity argument, okay? Especially when we have trig functions in pre-cal. And then, of course, when we're dealing with logarithmic and exponential functions, we can still interact with inequalities using multiplicity. So this is a very, very convenient tool for us. So I hope that this has been illuminating. Just remember, polynomials in general are not simple. However, the basic constructs that we talked about today can make the analysis of polynomials very straightforward. And so get used to looking for the multiplicities. get used to thinking about end behavior with the dominant term. And as you use the multiplicities, you can also think about moving to the descending form. But again, combine the transformations when possible. Think about maximum number of turning points just as an academic exercise, because in general, that is not a very useful tool, but not everything's going to be useful. So as you continue to work with this, we will add new ideas and build the theory to the point that we can actually factor things more effectively. For instance, we have some very good factoring tools now, and we are glad that we have them, but we want to be able to add a few more ideas so that we can get the maximum efficiency from our work. Okay, well, I'm done with this topic, and we'll see you later. Thank you.